Hello, welcome. We are the Ranger Arm team. We have been tasked with building a drone that features a robotic arm that can scan and manipulate the environment. Specifically, our team focuses on building the robotic arm incorporated with the AI vision system. I'm Isaac Yorkman.
I'm Jason Bartlett.
I'm Max. I'm Connor. Feel it. Motivation of the Ranger arm is to aid and assist in fields such as agriculture, repair, and accessibility. And the arm will be utilizing 5 degrees of freedom to accurately handle objects and position them effectively. And by incorporating technology such as machine learning, the Ranger arm will be able to handle tasks autonomously. And we also aim to perform these in difficult terrain and hard to reach locations.
So moving on to our team's main goal and objectives, we aim to build a multi-degree of freedom robotic arm equipped with a modular end effector, which is capable of performing a variety of autonomous tasks while mounted to the underside of a drone. Some of these specific tasks include autonomous leaf detection and sampling, where right now it is not a safe or viable option for agronomists to venture into a cornfield. Another one is vertical load suspension, dead hanging load, or something along the lines of a package carrying, and then just generic detection and sorting of a variety of different items.
So this project again features this 5 degree of freedom robotic arm that incorporates a dyno AI vision system to detect and position the robotic arm. To achieve this range of motion, we have incorporated the drone into 3 separate segments: the shoulder point, which accounts for both the pitch, which is this movement, as well as the yaw about the base, which is the rotation about the base. Then looking down at the drone, we have divided into the elbow, which accounts for a pitch right in the middle, as well as the wrist point, which accounts for a pitch at the wrist, which is this movement, as well as a yaw, which is a rotation about the central axis. To manipulate and grab our environment, we're incorporating a modular end effector, also known as the hand or the grasping device of the arm. We are incorporating a modular end effector as it allows us to design and build different grasping devices to better suit our needs, with the likes of which being a leaf sampling, deading, and just a general soft gripping device. And then to meet our Part 107 requirements of a 55-pound overall total weight, we have incorporated a lightweight design that is made out of carbon fiber and reinforced carbon fiber.
Yeah, so in order to build this robotic arm, we first studied some of the technologies that are out there currently. And today, most robotic arms will feature that shoulder, elbow, and wrist joint. The most common type of industrial robotic arm is a 6 degree of freedom one with spherical wrists. As for robotic arms on drones, Foxtech has built this. They are a company out of China. Their robotic arm was modeled after an elephant drone. Here are some pictures of the drone and arm doing tasks such as gathering a wet water sample and delivering a bag. And then in terms of computer vision, we looked at some different programs, but we have decided Dyno V3. It is an open source vision model developed by Meta. Dyno features self-supervised learning capabilities, and this allows Dyno to learn from data that you have trained it with. And self-supervised learning has been shown to be effective in tasks such as object detection and video tracking. For object detection, here we have it detecting the top leaf of that plant.
Yeah, so this is our current design. You can see we have the Ranger drone at the top connected to our Ranger arm. And we'd like to go into some of how we made some of these decisions with our arm. So this is our decision matrix. Here we compare 4 degrees of freedom, 5 degrees of freedom, and 6 degrees of freedom. And we have 4 categories: weight, range, power use, and machine learning. And we assign a weight to all of these and then ranked each of the 3 options. And this is how we chose whether we want to develop or drop an option. So in this decision matrix, we chose to develop 5 degrees of freedom.
So utilizing these decision matrices as well as our engineering knowledge, we have begun to develop this robotic arm. We are building a 5-degree of freedom ortho parallel design. So we have a shoulder joint, elbow joint, and wrist joint. Then through the combination of all of these joints and linkers, we have a 32-inch reach, meaning we can grab and position the end effector anywhere within a 32-inch radius hemisphere underneath the drum. So from our rotation at the base, we can rotate wherever we need, and then through our inverse kinematics, we can move the other linkages to get to any desired position in that hemisphere. Depending on the end effector, this robotic arm currently weighs 10 to 12 pounds and should be able to lift and move 10 pounds.
Yeah, so here's our first design solution, and this is for the base, which will be responsible for attaching to the Ranger drone, housing our first motor, and also housing our battery. Here you can see it is going to be a 3D printed part made out of PPA with carbon fiber. As you can see, the motor is mounted there, and then on the underside, you can see where exactly it's mounted to, along with the torque shaft that will harness the torque of the motor and give us that first yaw rotation.
So with all of the different motors, we have developed to both receive power from external motors as well as power in them. Seen in this diagram is the wrist, which connects to a preceding joint, which the top input shaft allows for the yaw rotation, and then the enclosed motor transmits the pitch. We in each joint, we have incorporated a driving board as well as an integrated gearbox. And then to access everything in this joint, we have removable end bells, seen at the very end with the mounting caps. Then to more evenly distribute the load, every joint has its own fork shaft, which is an aluminum assembly that is milled to have a 1/4-inch bolt as well as a beam profile. So with each integrated joint, we have an integrated motor as well. Specifically, we have selected motors from Cube Mars, the AK45-36, as well as the AK80-64. We selected these motors as they are brushless and footed motors, meaning we have a great power to weight ratio as well as the ability to control and position them. These motors incorporate a built-in driving board as well as a built-in decoder, so we are able to receive torque data, acceleration, as well as just general position of the motor. We also selected these motors as they have integrated gearboxes, which allows our output torque for each joint to be far greater than just the straight itself. And then again, we selected these because they have great power to weight ratios, with the largest of our motors weighing 800 grams and able to burst up to 128 meters of torque. So this allows us to pursue our lightweight.
Next, I will go into our design solutions for the various different types of end effectors. This first one being our soft gripper. You can see it's actuated using a stepper motor and a worm gear. It extends this linkage and uses those 3 flexible fingers to grasp around different abstract objects, and it's capable of handling objects with different textures. Our second end effector is this dead hang end effector, suitable for those vertical loads and or the package delivering. You can see with a spring-loaded torsional flipper there, it makes it for quick and easy disconnect and connecting. And lastly, we have this leaf snipper. It is a combination of both the PLA and PVA flexible grippers, as well as a cutting linkage to snip and be able to store those leaf samples. And to go along with those various different end effectors, we have a chuck adapter solution. This is bolted onto the end of the robotic arm, and utilizing a hexagonal 2-piece chuck collar, different end effectors can be inserted and tightened in quick and easy.
So to power and control all of our electronics, we're using a distributed system, which the main image processing as well as positional data handled away from the motors. We are utilizing the NVIDIA Jetson Orin to receive all of our video data, which gives us position as well as depth from our AI system. And then from this positional system, our inverse kinematics, we send data packets that tell the motors how to communicating to these motors by utilizing the CAN bus system, which means we are doing the main processing through our NVIDIA Jetson, which processes all of our AI, and then the Jetson sends small data packets to each motor, and all of the motors talk and receive from each other to know their full position of data. Once the motors have received their CAN packets, we are able to utilize the full power of a 6S LiPo battery to actuate and control these motors, but they're all rated for 20 volts.
Next up, we have our design solution for the camera system. Through our decision matrices, we chose to develop both the RGBD and stereo depth camera. These both perform the same task by giving us feedback as to positional data, both X and Y, and then a depth value. They just functionally perform it in a different way. RGB uses a time of flight sensing where it measures the time it takes for light to reflect off the object and bounce back to the lens. Whereas the stereo depth camera uses a binocular system where it triangulates the position using two cameras. Here on the right, you can see just a quick and simple smoke test we use to just get using these cameras and determine the depth of this black circle on a sheet of paper.
So the vision model that we chose to use was Dino version 3, and that was released here just in August. The version 3 was. And this is widely used in the industry of robotics. Even like Amazon Robotics uses this as well. So if you see on the right side here, those are our images of our corn plants left. And then the one on the right is the heat map that was generated. So the red is the positive identification of the corn plant top leaf. It's just the upper end of the leaf or corn plant. And then there's also a rectangular identifier box around that top leaf as well. So we were able to generate these images just through different training techniques. So negatives is something that's like bad in the heat map. We imported like white backgrounds, different soil types, and then different sky scenes so that we can use that as a positive. And then we also did different masking techniques. So it only really considers the top 30 or 40% of the image. And this is some of our sample code here on the left side. In Python.
And moving on to our outlook from this past semester, we began back in September with our systems definition and nailing down our scope for this project in preparation for the systems definition review, which led us to some preliminary CAD models and some preliminary reports and work for our preliminary design review in October. After that, we ordered parts, we revised our models further, bringing us to today, the Senior Design Conference, in preparation for our critical design review, which is early in December. And looking ahead to next semester, early in January, we'll be ordering parts and beginning our additive manufacturing process, as well as beginning assembly. And then into March, we will be finalizing our AI model and beginning our testing and implementation of that. Until early May, we will deliver our project to our sponsor.
Looking at our budget, we were given $40,000 by our sponsor, NASA, and there's two Ranger teams, the drone team and the arm team. So we get $20,000 of that allocated to us. And looking at our budget here, we have our motors, which is roughly $2,000, and that's for our big shoulder motor, and then our 4 smaller motors throughout the robotic arm. And then our hardware, which is around $170. Our electronics is kind of a big section that's around $3,000. One of the more expensive items for that would be our NVIDIA Jetson, and then also our cameras for our vision system. We have about $1,000 for material. That's between like carbon tubes, aluminum stock, and then our 3D carbon fiber filaments as well. And then our end effectors, 2 of which we will be purchasing. That's about $900, and this brings us for a total of around $7,100 for our entire arm. Any questions?
So we'll solely put the corn leaf example. It's gonna snip a leaf, hang on to it, and take it to some other drop box or something to collect the sample.
No, on the drone, there's an integrated hopper, so we will size this hopper to have the ability to hold 15. So we will land, analyze the leaf, snip it, and the arm will move backwards and put the leaf into the hopper on the drone. We didn't talk about it as it is designated to the drone.
You just said the word land. I want to clarify. Is this all happening with the drone floating in the air?
No, so the corn leaf analyzing, we couldn't, the drone has 32-inch propellers, so on that prop wash, we will not be able to accurately grab a single leaf. So for this task, we have foldable legs integrated into the drone, so it will land in the cornfield, and then the arm will be able to actually grab the leaf.
Let me look at slide 20. I'm not a machine learning vision expert, but I don't see too many cornfields where there's just one corn plant. Is it going to be harder for it to recognize the top leaf when it's in a field of corn plants?
This was mainly for training purposes. The ideal way to train a machine learning model, like Connor said, was to have simple and straightforward pictures and then be able to train with hundreds and hundreds. Right now, we're really struggling with finding grown and green corn. As one can imagine, it's nearly winter. So we're kind of doing the best what we can with what we have. We have plans in the future to go through something like Alibaba to get mock corn so that we can test our model. But yes, it is slightly different. We have tried applying this with some success to images with larger and more corn plants. But realistically, when the drone is landed, you'll be looking at a small area from top down, and you won't have to deal with the horizon being the entire full of corn plants, essentially. You'll be focused on an individual or a group of individuals.
With that, the camera is positioned at the very end of the effector. So as we get closer and closer to, we need the corn to first identify a spot, and then as the arm moves closer, we are able to get a closer and closer image that singles out a single.
Trying to picture this. Are the foldable legs like 8 feet tall?
Yep.
Okay. So it'll look like a daddy long legs type deal. Okay. One more question. Your base plate, your base design. Can you go back to that picture? Oh, there you go. So there's 6 smallish screws holding this thing on. Have you done some FEA on that to determine what that load is going to be?
Yes, the load we have on it right now is 20 pounds, which is about what we get for a maximum of the drone weighing 35 pounds. We only can carry, we only have pounds of that to stay under the Part 107 regulations. So we have a load of 20 pounds going down in that, and then also the torsion of the motive in that pipe there, just in case like the field shaft pops up.
My question is the 20 pounds always directly below it?
And
Is it always?
No,
Because don't you have to do the worst case where like the arm's out and it's got 20 pounds dangling on it?
yeah, there would be a moment there. That's something we'd have to.
right now, our simulated results are still being tested back for safety. Very acceptable. We simulated our material with 40% of the total strength available, and we're still getting factors to safety around 5.
For dead hang attachment too, that will only be supporting that load. It's always going to be down.
So for the 20 pounds, it will go straight down. But what's the max weight you're gonna actually be? Like when the arm itself is out, you got the weight of the arm, right?
Right now,
So the far bolts will have a lot more force.
We don't really have an application right now that it's applicable to, other than the weight of a lead up there.
Although if you go up.
I'm just concerned about the arm itself, because you said the arm's 12 pounds.
Right now I did go up and we did do the torque calculations for our motors, so. With our motors, they're at 50 torque, we should be able to about 20 radians per second squared. Just through our rated torque, but we have higher torque, and we will adequately size for that rated. So
Sure. I'm guessing the motors are okay. I was just more concerned about the strength of the base with those small.
they are grade 8.
No, the bolts won't. The tabs basically. It's a 3D printed part, so it's a crack.
Is cargo weight included in the like overall drone regulation?
Yes,
Okay.
the overall weight of this drone not exceed 55.
You go back to a FEA. What's up with that bottom picture? Like the scaling just seems kind of like what's the number we're looking at there with all that red?
The very bottom picture.
Yeah, the bottom right picture.
That is a factor of safety. For some reason, it designated our factor of safety, right? And we are looking at 9.3 for that factor of safety. That is our carbon fiber.
And that's dead hanging.
That is actually a bending moment.
Okay.
With a full 40 pounds applied to the end and one end being complete.
Okay, there will be a dynamic balance when you have arm connected to the quadrator. Then you have a dynamic balance. How do you overcome this problem to make the drone stable? It's not tilting because it's lightweight.
At the moment, Part 107 does not change the flight characteristics while it is flying. So this arm is not legally allowed to manipulate while the drone is flying. But in terms of the full, I guess once it's landed and the arm is actually, our kinematics are set up to constantly iterate upon the last position. So we are receiving acceleration data from the end nodes or the elbow. And then from that, we will be able to reposition the arm or offset this coverage. And then the entire structure is made out of carbon fiber, which allows us to have a very stiff material to try to offset some of that vibration compression.
I guess in this case, you need a flight controller to control
the drone. The actual Ranger drone itself does have an integrated flight controller. This flight controller is integrated directly to the jet. So they have a $2,000 flight controller that then can directly communicate with our Jetson to actually go on.
Are the 8-foot legs that you're landing on, is that going to affect your actual range of motion for the arm? Like, would it collide if you're trying to move from one position to another with the legs?
Right now, those legs are set 30 degrees, so there will be a small, I guess, like whatever that diameter system is that we will have to restrict. So we will not be able to move in that zone, but we will be able to move farther.
And you need to be 8 feet above with 30 angles. So these are going to be like 10 or 11 foot legs total. Wow. Okay.
The legs are foldable as they want to be able to analyze the corn in both just like brand new conditions as well as fully grown deeper. So I believe the drone team is working to make them scalable.
For corn testing, maybe you want to check with Plant Science because they have the greenhouses all over and they might be doing some different cropping growth of some corn, and maybe you can get some live corn testing this winter.
I just have one more quick question. So go to slide 20, one where you're sort of looking at the corn plant. So your real situation is going to be looking at it from. So it's gonna have to choose a corn plant first and then find the top piece of that one. So, how much different will this procedure be versus that procedure?
We're thinking of hard coding it so it does some sort of a scanning procedure where your camera will start above the leaf and then your arm will pan it down so it identifies the leaf and then down has your greatest chance of being. So there's going to be sort of an instruction protocol that goes along with it. It's not just going to be sitting there and then just have to look at the image. It's going to slowly pan into it. One approach that we're going to try out.
Also with like confidence too, if it's a certain percentage that's not confident enough, and we can always have it rotate. That way we can get a better image or better angle at it, so.
One more real quick one. Can you go back to 27? Where is it fixed? The top left.
So the top left is fixed at the very end. I fixed that geometry on just the back plate.
I'm looking at all the green arrows and the bolt holes. Are those where you fixed it?
The top left.
The top left image, I'm looking at all the green arrows and the bolt. So did you fix the cylindrical wall of the bolt holes?
Yes.
Is that how a bolt works?
We just thought that that's where the, where it would be held closest to,
That shouldn't you have like a washer shaped surface underneath?
right.
That's where a bolt would pull apart, right?
They are also shoulder bolts so that smooths and piece.
So you think the main fixturing the bolt will do is holding the cylindrical wall steady? So you know how I love boundary conditions, right? I love boundary conditions, and this is why it's important. This we need to simulate it, as accurate. So that just think about that a little bit.